So in this video, I will show how to find the eigenvalues for a system of differential equations. Now suppose we have a system that looks like this. X prime equals negative 2x plus 2y, and y prime equals 2x minus 5y. Now there are two differential equations in this system. Now how will we begin to solve for the eigenvalues? Well, we can actually rewrite this in matrix form. So we can write the left side as xy prime, and this would equal, we would have our coefficient matrix, which would be negative 2, 2, 2, and negative 5, multiplied by the vector xy. Now this is our system written in matrix form. Now we will assume, like we did in normal ordinary differential equations, for second order, recall that we would end up with a characteristic equation that would look something like this: r squared, minus 5r plus 2. That would be our characteristic equation, and we'd solve for r, and that would give us the value of our exponent. We do something similar in this case, however. We assume a solution of the form x equals ae to the lambda t, and we also have to assume a solution form for the y equation, and this will be y equals a different coefficient, however it will be multiplied by e to the lambda t as well. These lambdas are the exact same, and they're known as the eigenvalues of our system. Now how will we begin to solve this? Well, we can rewrite this, our assumed solutions, in matrix form as well to make it more clear. So matrix xy equals matrix AB multiplied by e to the lambda t. Now you've probably suspected this already, but we can actually plug this solution, expected solution, into our matrix form of our differential equation. Now what do we do about this xy prime here? Well, we can actually differentiate this. We can say that xy prime equals, we would just differentiate the e to the lambda t value, so we just get a lambda in front. Now we can then plug it in directly into our original, so we would get lambda ab e to the lambda t, and then equals negative 2, 2, 2, and negative 5 times ab e to the lambda t. Now we're all done plugging in. We notice first immediately that there is a factor of e to the lambda t on both sides, so we can cancel those. Now you may be tempted to just drop the AB vectors. However, you can't just cancel them because they are vectors and they do not have that property like these constants do. Now I'll erase these just to make it more clear. Now from this step, there are two ways to think about it. I will do the explicit way first and the linear algebra way next. I'll do the explicit way now. We can actually multiply these out to get our actual linear equations, so we can get lambda a equals negative 2a plus 2b, and then the second equation would be lambda b equals 2a minus 5b. Now we have two equations and three variables. However, we can make this more useful if we rearrange this to look like negative 2, bring the lambda a over to get negative lambda a plus 2b equals 0. Do the same with the bottom equation. We get 2a plus negative 5 minus lambda b equals 0. Now that we're at this step, I can use the property that the coefficient matrix, because if we back up, we are ultimately trying to find a and b, right? Now, there's the trivial solution of a and b both being equal to 0. We don't want that. That is trivial. That's not of interest. However, when will this system have a non-trivial solution where a and b are not equal to 0? Well, if we take the coefficients of a and b and we take the determinant, if we find that that does not equal to 0, equals to 0. So if we take the coefficient matrix and take the determinant, when there is a non-trivial solution, the determinant should be 0. Now, let me wall this off to make it more neat. We can say that the determinant of the matrix negative 2 minus lambda 2, 2, negative 5 minus lambda equals 0. Now what will this determinant be equal to? We'll first multiply the top left by the bottom right, and that will give us 10 plus 7 lambda plus lambda squared, and then multiply the bottom left by the top right, which will give us 4, and we subtract it, and this would be equal to 0. Now this would be equal to lambda squared plus 7 lambda plus 6 equals 0. And factor this to clean this up. Lambda plus 1 times lambda plus 6. Now this implies that our non-trivial solutions have lambda equals negative 1 and lambda equals negative 6. Now these two are our eigenvalues for our system. Now this is one way to think about it. There is another way to think about it. I will demonstrate that now. I'll erase the leftovers from this method. Now the second way to think about this, once we're at this step, once we have this, we can actually bring the left side over, and we can factor out the AB vector to get negative 2, 2, 2, negative 5. Remember, we factor out the AB vector, and then we'd be subtracting lambda. However, remember that we can't just subtract a constant from a matrix. It just doesn't work like that. So we can do the equivalent of multiplying by 1 for scalars, and we can multiply by the identity matrix. Remember that the identity matrix is a matrix with 1s on the diagonals and 0s everywhere else. This is an ugly identity matrix, but you get the idea. Now we can set this equal to 0. And what we get from this would be equivalent to our other method. This is simply a different way of thinking about it. would get our matrix -2 minus lambda. Remember, our identity matrix is 0 everywhere else that the diagonals. So 2, 2, and then -5 minus lambda. This is the same matrix that we calculated in our other method. Notice that this matrix is simply our coefficient matrix from the last time. In the next video, we will find the AB vector or the eigenvector of this system. Thanks for watching.